Welcome to CIMON's webinar today for a PID overview on PLCs. So some common applications that we see PID being used in would be temperature control, speed control, pressure control, and flow control. That would be an example of temperature control would be household thermostats, speed control would be cruise control, pressure control would be tank volume, and flow control would be chemical mixing. So your household thermostat would be a very good example for temperature. So when you're setting that dial to like 72 degrees Fahrenheit, and then your furnace or your AC turns on, that would be how PID is being used. It's being used within that controller of your household. And then for common equipment, along with those different apparatuses, we would have like furnace, air conditioning, motor, actuator sensors, different types of thermistor sensors, RTD, thermocouples, and thermistors. So that would basically insinuate that PID is a feedback mechanism type application where so it can actually control the manipulation value, the process value, and then the set value. And we'll get to those values later in the presentation. Also, we have an encoder, which is actually tracking the feedback going into your motor or your speed-based application that's tracking pulses, which typically couples with a motor or actuator. And then we have variable frequency drive, which is different than a servo drive. Instead of doing like positioning and speed, it primarily deals with speed control. So this is some common equipment that you'll find in PID applications. All right, so what is PID? PID, this is your formal definition of PID. It stands for proportional, integral, and derivative. There are different constants that I want to cover or different variables I want to cover with this formula or this application approach. So we have the SV, the PV, and then the MV, which stand for set value, process value, and manipulation value. SV is going to be your set value, which is the desired value for your steady state. Then we have the PV, which is going to be the feedback from the apparatus application, which goes into the formula, which generates your MV, your output that is calculated based on your SV and your PV. So an example of PID might be that the desired temperature in your house is set on the thermostat, which is your set value, your SV. The process value is going to be the ambient temperature in your household. And then the furnace or air condition turning on will be your MV. So all of three of these work in harmony together to actually create a full functioning PID apparatus application. Now, there are three other constants that I want to go through later in this presentation that will be KI, KP, and KD. These are manually adjusted after you do your auto tuning process to actually generate a very cohesive, or synergistic application. So for my visual learners out there, this is what a PID application would look like. On the left-hand side, we have the processing unit, so the CPU module. And on the right side, we have our control system. You might think of this as your furnace or your air conditioning unit. So on the left-hand side, we have a set value. That's your desired value, like you set on the thermostat. And then we also have the process value, which is being interpreted from a sensor in the control system that is being sent over an analog module and then converting it to like its binary value within the CPU, and then input into the PID operation, the PID formula, and then we generate a manipulation value automatically. And then that manipulation value will either tell the control system to turn on the AC, or it will tell it to turn on the furnace based on what your desired value is. So this is typically your feedback mechanism for the application of controlling temperature. And then this is another graphical representation of how PV and SV work together to actually receive that steady state. So you'll see that there's a little bit of curvature around the SV, and that's how we get the sinodal curve around the SV. So there is some drift that should be expected when you're cooling or heating. That's because you're trying to overcome momentum, because if you're up here with your temperature and you're turning on the furnace to, or you're turning on your AC to cool, you might have put it on full blast and it turned off right here, which is a little bit too much momentum. And then by the time it actually reaches the steady state or the set value, it went over a little bit too much momentum. So it stopped here, and then like it's cooling down, or the room still, and the room is still adjusting to it. And then it will eventually have a trough below the set value, and then we'll eventually hit another peak, and then we'll get this closed gap around the SV. And we can see the same thing for heating, whereas the momentum will be shifted upward instead of downward because we're using a furnace rather than an AC unit. So some common terms that we need to understand here is reverse action would mean cooling within the PLC software, and then forward action, remember, or that would be inferred as heating inside the software. So cooling and heating, those could be synonymous with slowing down or speeding up. When we think about motor control, reverse action is slowing down, and then forward action is heating up or speeding up rather. So this is going to be the formula that CIMON uses to calculate their PID or the PID output. So this is that Ki, Kd, and the Kp I was talking about earlier. I'm mainly interested in the first two, Kp and Ki. So Kp is how fast you're going to reach the steady state, and then Ki is how quickly we need to take off of the accelerator so we don't have too much drift from the steady state or too much drift from the SV so we get a proper steady state. Down here is the formula for direct action. So that's forward action or otherwise heating, speeding up. And then reverse action, that would be your slowing down or your cooling for the MV. So the MV is being calculated over here automatically. So this is what the PID program looks like inside the PLC software. On the top part, we see path calculation. So forward, the 0. So if you want to use D2 and you want to do a forward path calculation, so speeding up or heating, you're going to put the value 0 into D2. If you want to do reverse, you're going to put the value 1 in. Now, if you don't do a ladder diagram convert, you don't need to worry about those numbers because you're selecting like a face value here. You're selecting forward or reverse. But if you do a ladder diagram convert, this option up here, you will need to make sure that you're putting the correct value in. So 0 for forward and 1 for reverse. So forward means heating and reverse means cooling. Now, CIMON's PLC can manage up to 32 different loops, and they can auto-tune each one of them. So that's how we can create steady states for 32 motors, 16 AC units, what have you. It can be very dynamic in that the manner of approach. And then you can also control the number of loops being scanned. So if you want like 4 loops being scanned, that means that loops 1 through 4 will be scanned, and then 5 through 8 will be scanned, and then 9 through 12 will be scanned in that order. So you can control the intensity of your application with that way. And then there's 2 other operands here that I want to look at. I want to look at the PID INT, which is where you're going to buffer all of your constants into the PID program prior to the PID calculation initializing. So once the PID calculation starts, it's going to generate an MV based on your SV and PV and your PID INT values. So your SV being that set value that you want to reach, and the PV being your ambient environment that you're receiving. It's that feedback that you're getting. It's the feedback that you're getting from your environment, whether you're using a sensor or whether you're using a field device such as like an encoder. And then we already spoke about auto tuning. It generates the best constant values for the application. I would want to append that. I would say it helps you generate the best constant values because the best constant value generation is going to be coming from manual intervention. So auto tuning is going to help you and guide you get to like the ballpark range where you should be at. And then you yourself are going to change the KP, KI, and KD to meet your application needs. And then LD convert, we already went over this. It transformed this GUI interface, this one right here, into a ladder diagram. All right, so an example configuration with using the software is that you'll have an SV, which you can set with D100. And then the process value, you can have it come from an analog card, and then the manipulation value is going to be sent to an analog card. So that's why we're using the instructions from and to. So from is going to be grabbing it from the analog card, and to is going to be sending it to the analog card. So RTD, that's your temperature sensor. That's going to be grabbing it from your RTD sensor within the room, measuring your ambient temperature. And then you're going to look at this analog here, analog output card here, DA, so analog output. It's going to be sending a different magnitude of response to your heater. So it's telling it to, maybe generate 100 degrees Fahrenheit or generate 80 degrees Fahrenheit. It can have that dynamic control, or it can have a static control. Most patrons typically side on doing a static control because it's a cheaper route when you're actually controlling temperature or speed. So for example, most AC units in your house only generate one static temperature. So like that's why if you stand near the AC unit, it's very cold. And even it doesn't matter how close you are to the set value, it's still going to be generating that very cold value because the engineer decided to opt for a static AC unit instead of a dynamic AC unit. So meaning like, let's say they chose a value of 60 degrees Fahrenheit and you're wanting to get to 72 degrees Fahrenheit from a temperature of 90 degrees, it's going to be outputting 60 degrees Fahrenheit all the way up until 72. It's not going to like increase in temperature the closer you get to 72. So like it might be 60 at first, then as you're dropping down to like 75, it's not going to increase to like 65, 70 degrees to get closer to meet it in the middle. It's just going to be a constant 60 degrees Fahrenheit. And then that is how you actually get drift because you have a lot of momentum and you're only outputting a single temperature. So there's two ways to control PID. You can either do a static output. So you have a static like 60 degrees Fahrenheit for your AC unit, or you can have a dynamic approach, which is not as cost effective because you have to source an AC unit that actually has dynamic control, which is not, it's pretty rare out there in the market. It's a lot easier to do this when you're thinking about speed or motor control. So there's two ways to combat a PID application. You can do static or dynamic. And again, we're going to be using from and to instructions. So from being our process value, and then to being our manipulation value. So we have something else called relay tuning. So relay tuning, I would use it with very slow moving applications because if you're using a fast application and you try to do auto, or if you try to do a slow application with auto tuning, it is going to be calculating undefined parameters based on how our formula is presented. And then it's just going to fail to auto tune every single time. But if you do relay tuning, it will take into account that you have a slow application and it will do these pulses rather than a dynamic like curve. Instead of like an exponential curve or a linear line, it'll just be it'll be a pulse. And you'll get this like weird pulsing signal. So that can be selected here on auto manual. So if you double click on this operand down here, you can select between auto tuning or relay tuning down here in the tuning options. But most applications are pretty quick and auto tuning will fit. But I've encountered like extruder applications where it's pulling out metal bars and it's slowly heating up. Those type of applications might require a relay tuning process. So you can use PID with a PLC simulator to kind of see how the behavior works. So I'm going to do that right now so you can kind of see like what you would look at on terms of a graph. So we'll show kind of like a preliminary example for your application here on the software. So if you haven't had a chance to open up the CIMON software, it looks somewhat like this. You go to File, New Project, choose my PLC. I'm going to press OK. I'm going to go through these steps a little bit quick because I don't need them. New program, I'm going to create a very basic scan program and not put anything in it. And then I'm going to create a new program for PID. I'm going to press OK. So I'm going to leave everything as is, and then we're going to go straight to the simulator. We're going to download that to the simulator and then see how this behaves in real time. Let's do its magic. It's going to start downloading. It's almost done. And notice that I did not do any ladder diagram convert. I can just leave it in its GUI interface origin. So we're going to go to monitor view, mon view, and we're going to look at it from the graphical representation here. But aside from that, I'm going to open up the memory monitor as well. So you can kind of see I'm going to change values as time goes on. So we're going to go to the D device, and we're going to be at D100 right here. And we're going to set a value. We're going to start auto tuning. We're going to set a value of 100. So you're going to see 100 populate into D100, and you're going to see that the MV shot up to 16,000 right away. So the MV is like, oh, the PV is less than 100. I need to be at the highest magnitude to actually get to that. So we're going to actually give a feedback to it now. We're going to start increasing. We're going to start increasing and faking the PV value. And then the closer I get, we'll see that that value of the MV will start shooting down. So it was auto-tuned. And then I'm going to go up to the SV. And you can see that the MV started changing right away. So we're going to get a little bit closer. And then a little bit closer. Then this close. And we can see that the MV is dropping down drastically. And then we'll go up to 100. And then we're going to simulate the whole drift behavior because we're going to overshoot it because of momentum. And we should see that it should drop down even more. And the fact that it's not going down should indicate you need to keep going down further. And then we're going to go down to 105. And it might increase a little bit because it's expecting that it's going to overshoot downward. So then we get this kind of like process value that's being that's going up and down, trying to reach the steady state of 100 that's way down here. So we can't really see down there because the manipulation value is the whole y-axis. So I chose a pretty poor number. I chose set value. But the green line and the red line should be on top of each other down here. We can kind of show that in a different manner. So I'll start auto tuning. Let's do a better number. Let's do 3000. So we can see that the red value is here now. So we want to pay attention to that green value, the process value. So we're going to start pushing that up to 1000. And then we're going to push it up to 1200. And then maybe 1700. So this is not practical by any means because a real application would move a lot slower than this. So it does say I failed, but we're going to ignore that for right now because I definitely did not move correctly. But the whole point is to get the PV as close as possible to the SV, and then the MV will generate a response based on that. So it's going to stay 0 because I'm too far beyond it. Now, if I go down to 2700, the PV should shoot up again. And you'll notice that the green line is trying to try to be as close to that, that red line as close as possible. If I get to 2900, it might just turn back to 0. So it's treating it like a digital output. It's like just off and on, off and on. And then now we have some dynamic variability now. So that's pretty much PID. It's hard to simulate PID, like I said, to err as human. But manual intervention is never the way to go when you're trying to control your cruise control or whatever with your foot, because a machine is most likely to be you. The only manual intervention that I really recommend with this is going to be setting your KD, KP, and KI. So those three. You'll see that the values over here are different than what I originated from. So 30,000, 19.2, and this one stayed 0 because I left it as a non-zero, or I left it as a 0 value. So if we go back to the presentation, I think that might be it. Second. Okay, so yeah, that is it for today. I appreciate everyone for stopping by. Next time I might have an actual PID apparatus set up for us. And thank you so much for everyone showing up. So I hope you have a great rest of your day. I'll be staying around for the next 5 minutes if you have any questions. Other than that, we'll send this recording out and we'll go from there. So have a great day, guys.